Hello young mathematicians, and welcome to number theory and cryptography. In this lecture, we will investigate more of the brilliant ideas of Euler, the incredible genius. The problem that we will investigate together was suggested to Euler by the French mathematician Philippe Naudet. This latter asked Euler in a letter about the number of ways one could write a positive integer as the sum of distinct positive integers. Euler was 33 years old, and it only took him few days to respond brilliantly to this problem. So if you want to know why, I suggest you take a deep breath, because Euler uses heavy tools and an incredible ingenuity to solve the problem. So the question we're going to answer here is in how many ways a positive integer could be written as the sum of distinct positive integers. Let us denote together d of n, the number of ways in which a positive integer n can be written as the sum of distinct positive integers. Now, if n is equal to 1, the only way to write 1 as the sum of distinct positive integers is 1, which means that d of 1 is equal to 1. Now, if n is equal to 2, one can write 2 as a 2 or as a 1 plus 1, but 1 plus 1, they're not the sum of distinct positive integers, so we erase this 1, and d of 2 is equal to 1 as well. Now, if n is equal to 3, one can write 3 as a 3, or as a 2 plus 1, or as a 1 plus 2, but that's the same thing, or as a 1 plus 1 plus 1, but we cannot take 1 plus 1 plus 1 because the integers are not distinct. So d of 3 is equal to 2. Now if you go further, for n equals to 4, we have 4, but we also have 3 plus 1, we have 2 plus 2, but they're not distinct. We have 2 plus 1 plus 1, but we cannot take this as a solution, and thus we get that d of 4 is equal to 2 as well. Now for n equals to 5, 5 is equal to 5, or it is equal to 4 plus 1, or 3 plus 2, and you can check by yourself that these are the only ways in which we can write 5 as the sum of distinct integers. So d of 5 is equal to 3. Now if n is equal to 6, one finds 6, 5 plus 1, but we can write 5 as 4 plus 1, and if we replace 5 by 4 plus 1, one gets 4 plus 1 plus 1, which does not hold. But how about replacing 5 with a 3 plus 2, in which case one gets 3 plus 2 plus 1, and this is the sum of distinct integers that yields 6. Now if you go further, we know that 6 is 4 plus 2, and these are the only combinations in which one can write 6 as the sum of distinct positive integers. Thus, d of 6 is equal to 4. I suggest you go further by yourself and check more computations of d of n, but these are tedious computations, and the natural question is there a systematic way in which one can compute d of n more easily than checking all the combinations in which n can be written as the sum of distinct positive integers? Well, Euler gave an incredible idea to compute d of n in a systematic way. Euler's idea was to take the infinite product p of x, which is equal to 1 plus x times 1 plus x squared times 1 plus x cubed times 1 plus x to the 4, and so on and so forth, infinitely of course, and he asserted that if we expand this infinite product, one gets here 1 plus d of 1 times x plus d of 2 times x squared plus d of 3 times x cubed plus d of 4 times x to the 4th, and so on and so forth. But of course we have to do the expansion infinitely. Oh really? Let us try to expand the first two here. So if you take 1 plus x times 1 plus x squared, one gets 1 times 1, which is 1, plus x squared plus x cubed. Now if you go further, 1 plus x times 1 plus x squared times 1 plus x cubed, and expand this. Of course you have to do it by yourself to see how to expand these algebraic identities. What we do is 1 goes to 1 and then it goes to 1, so we get a 1 times 1 times 1, and then 1 goes to 1, and from here it goes to x cubed, so we get 1 times 1 times x cubed. Then this one here goes to x squared, and x squared goes to 1, in which case we get 1 times x squared times 1. Then 1 goes to x squared, and x squared goes to x cubed, in which case we get plus 1 times x squared times x cubed. And now it is x that travels to 1, and then 1 travels to 1, so we get plus x times 1 times 1. This same x travels to 1 and then travels to x cubed, in which case we get plus x times 1 times x cubed. And now instead of traveling to 1, x will travel to x squared, and x squared will travel to 1, so we get plus x times x squared times 1, and finally plus x times x squared times x cubed. So we get here 1 times 1 times 1, which is equal to 1. Terms in x, there is one only way to get an x, which is x times 1 times 1. So we have 1x here. There is also one only way to get an x squared, which is here. So we get plus x squared. How many ways can we get an x cubed? We have an x cubed here, but we also have x times x squared, which is plus x to the 2 plus 1. Then we get x to the 4th, which is x to the 1 plus 3. The term here. In this product, the only way to get x to the 5th is with x squared times x cubed, which means we have plus x squared plus 3, and one only way to get x to the 6th, which is x to the 1 plus 2 plus 3. Do you see what I'm seeing here? The more we go further, the more these sums of distinct integers of a given power appear, and this what was suggested by Euler actually. Notice as well that in the first product there was only one x cubed, while in the second product another x cubed appeared, which is x to the 2 plus 1. I claim that if we go further and multiply 4 terms, then we cannot get any more x cubed, but we will get more x to the 4th and other terms. Let us now multiply the 4 first factors and see what happens. So we have 1 plus x times 1 plus x squared times 1 plus x cubed times 1 plus x to the 4th is equal to 1 travels to 1 and then travels to 1 and then travels to 1, which gives 1 times 1 times 1 times 1 again. The last one, instead of traveling to 1, it would travel to x to the 4th, in which case we get 1 times 1 times 1 times x to the 4th, and then one gets plus 1 times x cubed, which will travel to 1, plus here 1 times x cubed, which would travel now to x to the 4th, and now plus 1 times x squared times 1 times 1, and then plus 1 times x squared times 1 times x to the 4th, and then plus 1 times x squared times x cubed times 1 plus 1 times x squared times x cubed times x to the 4th. And now it is the x here that would travel all over the other factors, which gives plus x times 1 times 1 times 1. I'm not afraid of computations, as you can see. Plus x times 1 times 1 times x to the 4th plus x times 1 times x cubed times 1 plus again x times 1 times x cubed times x to the 4th plus x times x squared times 1 plus x times x squared times x cubed times 1 plus x times x squared times 1 times x to the 4th plus x times x squared times x cubed times x to the 4th, and we're done. I wrote things down again, and we get here a 1, which comes from 1 times 1 times 1. And then how many terms in x? Actually, one single term every time. So we have plus x here, and then one only x squared, which is here. So we get x squared, and then plus x cubed, which is here, plus x times x squared, which is x powers 2 plus 1. Notice the same expansion as the one before, but we will get more terms in x to the 4th and x to the 5th, and so on and so forth. And this is why we have to expand p infinitely to get d to the n every time in front of x to the n. So here we have one term in x to the 4th, so plus x to the 4th plus x to the 1 times x to the 3, so x to the 3 plus 1, and that's all. Remember that d of 4 is equal to 2, so we cannot get any further. And now we get x to the 5th from x squared plus 3, and from x to the 1 plus 4, so plus x to the 1 plus 4. And that's all we can get here. Notice we cannot have x to the 5th. And this is because there is no x to the 5th here. And so if you go further, we see that we have x to the 6th here, which is x squared plus 4 plus x powers 1 plus 2 plus 3. And that's all we can get for 6 for now. Now here we have an x to the 7th, so plus x cubed plus 4, and another x to the 7 here, which is x powers 1 plus 2 plus 4, and that's it. That's it for now, of course, because if you expand more, we will get more terms in x to the 7th. Now we get 8 from this, which is 1 plus 3 plus 4, and that's the only way we could get an 8, so we have plus x powers 1 plus 3 plus 4. Same thing for x to the 9, which we can get from here, so plus x squared plus 3 plus 4, and then last one is here, which is x to the 10th. So we have plus x powers 1 plus 2 plus 3 plus 4. They're just computations, right? But they're very instructive, and we should now inspect why in front every x to the n here, there should be d to the n, which is the number of ways in which n can be written as the sum of distinct positive integers. So if we get back to our infinite product, Euler multiplied out all of them and collected like powers of x, and he noticed that every time he gets d of n in front of x to the n. For instance, there is only one way to get a 1, which is by multiplying all the 1s all together, and this infinitely. Now there is also one way to get an x, which is to multiply an x by a 1 and then by all the other 1s infinitely still. This is because if you multiply an x by a 1 and then get to the x cubed or another power of x, it is impossible to get an x. Thus, d of 1 is equal to 1. Now, same thing here. There is only one way to get an x squared from this multiplication, but there are two ways to get x cubed, and this is why d of 3 is equal to 2 actually, and this is either by multiplying 1 by 1 and then by x cubed and then get all the other ones, or by multiplying x by x squared and then by all the other ones, and these are the only ways to get x cubed. Now to get an x to the 4th, either we multiply 1 by 1 by 1 and then by x to the 4th and then collect all the other ones, or we would do x times 1 times x cubed and then collect all the other ones. And these are the only ways one could get x to the 4th as the sum of distinct positive integers. Same thing with x to the 5th. Either it is only 1s and then x to the 5th and then only 1s, or a 1 then an x squared and then an x cubed and then only 1s, or an x to the 4th and only 1s. Thus we get either 5, either 2 plus 3, or 1 plus 4, and that's it. Hence, d of 5 is equal to 3. I hope it is obvious now for you that if we multiply out all the terms infinitely, then one gets the same number of x to the n as the number d to the n, which is the number of ways one can write the positive integer n as the sum of distinct positive integers. When we multiply all these out, actually, we get distinct positive integers, and this is because in each factor of p, there is a different power of x. Now be careful, because we do not know what does it mean to multiply out infinitely many times a product, but Euler actually had his reasons to do so and knew that there is no danger of multiplying these factors all together, because we will see together that it is wrong to consider infinite sums or infinite products as finite ones. Algebra is actually not the same. But here, Euler knew it was the same because he had his own secret tools. I wrote a computer program in Python for this purpose, and the first function here, product, will multiply two polynomials. On Python, a polynomial is just a list of numbers, which is the list of its coefficients. Here, n is the degree of p, m is the degree of q, and these for loops makes it possible to compute the product of p and q. The output will be a list, which means another polynomial, which is p times q. Now here I wrote another computer program which returns the polynomial p 1 plus x for n equals to 1, 1 plus x squared for n equals to 2, 1 plus x cubed for n equals to 3, and so on and so forth. I remind you that a polynomial is only a list of its coefficients, so 1 plus x squared, for instance, is 1, 0, 1, because 1 is the constant, then 0 is in front of x, and another 1 in front of x squared. Thus, for example, 1 plus x cubed is 1, 0, 0, 1, which means that 1 is the constant, the double zeros are in front of x and x squared, and 1 in front of x cubed. Now, product Euler computes the product of the n first factors of p of x. Let us now see on the shell how things works out. First, I would like to check my function product with two polynomials. For instance, x minus 2 times x minus 3. So I tell it product of two lists, of course, because a polynomial is a list. The first list contains minus 2 for the constant, and because it is x minus 2, the coefficient in front of x is 1. So the first polynomial is minus 2, 1. The second polynomial is x minus 3, which means minus 3, 1 here. After multiplication of x minus 2 by x minus 3, we should get x squared minus 5x plus 6, which means the list 6 minus 5 and 1. Is this so? Let us see together. Sure, 6 minus 5 and 1, which is the polynomial 6 minus 5x plus x squared, or equivalently x squared minus 5x plus 6. So my function product works very well, and now I would like to see what does poly-Euler do. So poly-Euler of 1, for instance, gives us 1, 1, which is the polynomial x plus 1, the first factor here in p of x. Now if you check it poly-Euler with 2, for instance, one gets 1, 0, 1, which means x squared plus 0 times x plus 1, which is x squared plus 1, meaning the second factor in our product. Poly-Euler of 3 gives us 1, 0, 0, 1, which is x cubed plus 1. Now product Euler of n, if I check it with 1, it gives us 1, 1, which is 1 plus x, which means it did not multiply anything, and it gives us the first factor of p of x. Now product Euler of 2 should give us 1 plus x times 1 plus x squared, which is equal 1 plus x squared plus x cubed. Is this so? Let us check. Sure. So we get here x cubed plus x squared plus x plus 1. Great job. Now we check product Euler with 3, which should give us 1 plus x times 1 plus x squared times 1 plus x cubed. So what we get here is x power 6 plus x power 5 plus x power 4 plus 2x cubed plus x squared plus x plus 1. Is this true? Actually, it is, because our previous computations showed that 1 plus x times 1 plus x squared times 1 plus x cubed is equal to 1 plus x squared plus 2 times x cubed plus x to the 4th plus x to the 5th plus x to the 6th. Great. So now I would like to compute product Euler of 10, for instance, and this is what we get. So this is a huge polynomial, but the coefficients here are 2, 2, 3, 4, 5, and they are the same coefficients as here, 1, 1, 2, 2, 3, 4, and so on and so forth. But how on earth did Euler think of his polynomial and that multiplying all out and collecting like powers of x would give d of n? He was an incredible genius, and that's the bottom line. Part 1 of our exciting lecture ends here, and don't go too far, because in part 2, Euler goes even further and proves something really unexpected. Thank you for listening.